The 1976 work by Michael Atiyah and Isadore Singer, known simply as the index theorem, represents the consolidation of a profound mathematical synthesis that reshaped the landscapes of geometry, topology, and analysis. This essay undertakes rigorous evaluation of the internal claims, logical architecture, and conceptual frameworks presented within this monumental achievement. The focus remains exclusively on the arguments as constructed by the authors, tracing the progression of their reasoning from the initial formulation of the problem to its eventual, multifaceted resolution. We will proceed through a direct examination of the theorem's constituent parts, assessing the coherence and power of each claim in building the final intellectual edifice. The inquiry is one into the internal mechanics of a masterpiece, seeking to understand the work on its own terms and evaluate the strength of the intellectual machinery it introduced to the world of mathematics. Section 1. The foundational claim of index stability. The work commences by framing the central problem. It considers a smooth, compact manifold without boundary, upon which is defined an elliptic differential operator. This operator, let us call it E, maps sections of one vector bundle, E, to sections of another vector bundle, F. The initial claim presented by Atiyah and Singer is that the analytical index of such an operator, a quantity, defined as the dimension of the kernel of D minus the dimension of the cokernel of D, a well-defined integer. This claim itself is a cornerstone. The ellipticity condition ensures that the kernel and cokernel are finite-dimensional spaces, a result flowing from the theory of Frobenius operators. The deeper, more operative claim within this introductory section is the stability of this integer. Atiyah and Singer assert that the index remains invariant under continuous deformations of the operator. This means that if one were to smoothly perturb the coefficients of the operator D, the resulting integer value would hold constant, provided the ellipticity condition is maintained throughout the perturbation. The evidence for this assertion rests on the open nature of the set of Frobenius operators and the discrete nature of the index. A continuous path of operators yields a continuous path of Frobenius operators, whose index, being an integer, must therefore be constant. The evaluation of this opening gambit reveals its strategic brilliance. By establishing the index as a deformation invariant, the authors immediately elevate the problem from the realm of pure analysis to one of topology. An object that is insensitive to small wiggles and changes is fundamentally topological in nature. This claim successfully reframes an analytical question, the computation of the dimensions of solution spaces, into a topological one, a quest for a global, invariant quantity that depends solely on the underlying manifold and vector bundles. Section 2. The construction of the topological counterpart. Having established the topological nature of the analytical index, the author's next major claim is the existence of a purely topological formula that computes this same integer. This is the theorem's core promise. The construction of this topological index begins with the principal symbol of the operator D. For each point on the manifold and each cotangent vector at that point, the symbol is a linear map between the fibers of the vector bundles E and F. The ellipticity condition translates to the assertion that this symbol map is an isomorphism for all non-zero cotangent vectors. This property is pivotal. It allows Atiyah and Singer to construct a specific topological object. The symbol defines a continuous map from the sphere bundle of the cotangent space of the manifold to the space of isomorphisms between the fibers. This data, they claim, can be encoded within the framework of topological K-theory. The work posits that the symbol of an elliptic operator naturally defines an element in the K-theory group of the cotangent bundle of the manifold. The evaluation of this step shows an immense conceptual leap. The introduction of K-theory was a masterstroke of abstraction. This branch of algebraic topology, relatively new at the time, provided the precise language needed to handle families of vector bundles and their equivalence classes. The claim that the symbol defines a K-theory class is robust and provides the essential bridge. The subsequent claim is that one can apply a K-theory map, known as the topological index map, to this element. This map takes the K-theory class of the symbol and produces an integer. The proposed formula for the topological index involves pairing this K-theory class with a fundamental class, and then applying standard tools from algebraic topology, specifically the Chern character and the Todd class. The full expression asserts the topological index equals the integral over the manifold of the Chern character of the symbol's K-theory element, multiplied by the Todd class of the manifold's complexified tangent bundle. The argument here is one of structural correspondence. The framework of K-theory possesses the correct formal properties and algebraic machinery to convert the data of this symbol into a single integer in a way that is manifestly a topological invariant. Section 3. The central mechanism of the cobordism proof, the most ingenious element of the original proof, presented across the seminal papers, is the claim that the equality of the analytical and topological indices can be demonstrated through a cobordism argument. This section of their work makes a profound methodological assertion. Atiyah and Singer construct a new quantity, the difference between the analytical index of an operator and their proposed topological index for that same operator. They then claim that this difference defines a ring homomorphism from the cobordism ring of manifolds to the ring of integers. A brief explanation of the terms is necessary. Two manifolds are said to be cobordant if their disjoint union forms the boundary of a single, higher-dimensional manifold. The set of equivalence classes of manifolds under this relation forms a ring, the cobordism ring. The core of Atiyah and Singer's claim is that their index difference function respects this structure. If a manifold M is the boundary of another manifold W, they show that the index difference for any operator on M is 0. This has a staggering consequence. According to the deep work of René Thom, the entire cobordism ring is generated by a small, finite set of specific manifolds, such as complex projective spaces. Therefore, if Atiyah and Singer can demonstrate that their index difference function is 0 for operators on these specific generator manifolds, the homomorphism property guarantees that the difference must be 0 for all manifolds. This argument effectively reduces an infinitely complex problem, proving the theorem for every possible manifold and operator to a finite set of concrete calculations. The evaluation of this claim is that it is an argument of unparalleled elegance and power. It sidesteps a direct, frontal assault on the equality. It instead builds an abstract machine that proves that if the theorem works in a few test cases, it must work universally. The validity of the cobordism invariance of the index difference is a technical tour de force, relying on constructing a specific elliptic operator on the bounding manifold W and analyzing its boundary value problem. This piece of their work is perhaps the most celebrated for its cleverness and its ability to leverage deep structural results from topology to solve a problem. In analysis, Section 4. The argument's concrete realization and verification. Following the abstract machinery of the cobordism argument, the work must provide its concrete foundation. The claim here is one of successful verification. The entire logical edifice of the cobordism proof rests on the assertion that the Atiyah-Singer index formula holds true for the generating manifolds of the cobordism ring. This section of their work transitions from abstract theory to direct computation. For specific operators on spaces like even-dimensional spheres and complex projective spaces, they perform the calculations for both the analytical and topological indices and show they are equal. For example, they consider the Dolbolt operator on complex projective space. The analytical index of this operator is known from the Hirzebruch-Riemann-Roch theorem, a major precursor to their work. The authors then proceed to compute their topological index formula for this specific case. The computation involves a detailed analysis of the Chern character and the Todd class of complex projective space, culminating in an integer that matches the known analytical result. This meticulous verification is a critical part of their argument. An evaluation of this section finds it less glamorous than the cobordism argument. yet absolutely essential for its logical closure. Without this successful verification, the cobordism machine, however beautiful, would lack its fuel. The claim is that these specific calculations are both correct and sufficient. The reception and scrutiny of these calculations by the mathematical community confirmed their correctness. The sufficiency is guaranteed by Thom's theorem on cobordism generators. This part of the work demonstrates the author's command over both abstract theory and the concrete calculation of topological invariance, showcasing the theorem's practical computability in key situations. It provides the empirical evidence, within the world of pure mathematics, that their grand theoretical structure is firmly anchored to reality. Section 5. An alternative logical pathway via heat kernels. A subsequent development, representing a significant evolution of the proofs in telelogic, was the introduction of the heat equation method, developed by Atiyah, Bott, and Vijay Patodi. This constitutes a new and distinct claim about the nature of the index. The central assertion of this alternate proof is that the index of the operator D can be computed as the supertrace of a related heat kernel operator. Specifically, one considers the operator exponential of minus t times d star d, where d star is the formal adjoint of d and t is a positive time-like parameter. This is the solution operator for a generalized heat equation on the manifold. The claim is that for any positive t, the index of d is precisely equal to the supertrace of this heat operator, which is the trace of its action on one space minus the trace of its action on another. This is a remarkable statement in itself. The more profound claim follows. As the time parameter t approaches zero, this heat kernel has an asymptotic expansion. Atiyah, Bott, and Patodi claim that the constant term in this asymptotic expansion, when integrated over the manifold, yields the index. Furthermore, they were able to show that the integrand of this term is a local expression constructed purely from the symbol of the operator and the curvature of the manifold. This local expression is precisely the same integrand that appears in the Atiyah-Singer topological index formula. Evaluating this claim reveals a conceptually different, and in many ways deeper, justification for why the theorem is true. The cobordism proof was global and relied on topological arguments of cutting and pasting manifolds. The heat equation proof is local. It demonstrates that the global topological index is actually the sum, or integral, of a locally defined geometric density. Each point on the manifold contributes a small amount to the index, an amount determined by the local geometry at that point. This perspective was revolutionary and forged an immediate, powerful connection to theoretical physics, where such local quantities and path integrals are fundamental tools. The claim that a global topological number arises from integrating a local geometric formula provided a new intuition and a powerful new computational method that has been immensely fruitful. Section 6. The generalization to families of operators. The framework of the index theorem was further extended to a more general and powerful setting, which constitutes another significant claim about its scope and structure. This is the Atiyah-Singer index theorem for families. Here, the work considers not a single elliptic operator, but a continuous family of elliptic operators parameterized by some auxiliary topological space, say Y. The claim is that the analytical indices of the operators in this family, instead of forming a set of integers, can be bundled together to form a formal difference of vector bundles over the parameter space Y. This object is an element of the K-theory group of Y. This is the analytical index for the family. The corresponding claim is that there exists a purely topological index for the family, also an element in the K-theory of Y, constructed from the symbol data of the entire family of operators. The theorem for families asserts that these two K-theory elements are identical. The evaluation of this generalization is that it represents the theorem in its most natural and powerful form. It subsumes the original theorem as the special case where the parameter space Y is a single point. The proof of the family version required a significant extension of the original techniques, further solidifying the essential role of K-theory as the correct language for the problem. The claim's validity demonstrated that the correspondence between analysis and topology was not merely about a single integer but about a much richer algebraic structure. This generalization proved to be of immense importance, finding applications in areas like gauge theory and the study of moduli spaces, where one naturally encounters families of operators. For instance, a family of Dirac operators parameterized by a space of background gauge fields. The family's index theorem thus represents a claim about the deep structural consistency of the analysis topology dictionary established by the original result. In conclusion, the body of work culminating in the Atiyah index theorem stands as a uniquely coherent and powerful series of claims. The initial assertion of index stability correctly identifies the problem's topological soul. The construction of the topological index through K-theory provided the exact language and tools necessary to quantify this topological information. The logical architecture of the cobordism proof offered an argument of stunning elegance, reducing a universal problem to a finite, verifiable set of calculations. These calculations were then executed with precision, grounding the abstract structure in concrete reality. The subsequent heat equation proof provided an entirely new, local perspective that deepened the understanding of the theorem's origins in geometry and forged powerful links to physics. Finally, the generalization to families demonstrated the true structural depth and scope of the correspondence they had uncovered. The evaluation of each successive claim reveals a step-by-step construction of an unassailable mathematical truth, with each new layer of argument reinforcing and illuminating the others. The work's enduring significance comes not only from the final formula, but from the cascade of powerful ideas and techniques it unleashed. It established a new paradigm, a dictionary for translating intractable problems in analysis into computable questions in topology, a legacy whose implications continue to unfold across the mathematical sciences.